So we are trying to understand active regions. The magnetic fields are generated by dynamo action inside the convection zone of the sun, and the fields erupt through the surface either because of magnetic buoyancy or because they're brought up just by advection due to the convective upflows, and they come up through the surface and they produce the patterns that we see at the surface. We see magnetic fields erupting on all scales, from very tiny things of the order of tens of kilometers up to the large active regions, which are order of hundreds, thousands of kilometers. And when the new field that emerges through the surface interacts with the already existing field in the atmosphere and the chromosphere and the corona, you get a lot of stored magnetic energy, and that can be released very suddenly, and that produces the explosions. And so what we're doing is magneto-hydrodynamic radiation simulations to try and model, for myself, a piece of that process. Other people are trying to model the other aspects of it. What I'm looking at is taking the field that's produced by the internal dynamo, how does it come up through the surface, and then other people will then take those things and try and model how that produces, what kinds of structures that produces in the chromosphere and the corona. And the challenge is, as Brian was saying earlier, somewhat similar. First place, it's the physics. In order to have something that's reasonably like the sun, you need to include a lot of the physics of the atoms, the excitation and ionization. You need to include the radiation emission and absorption and transport, and it's a very, very turbulent medium. Also, as in the case for the galaxies and star formation, there's a wide range of spatial and temporal scales. So at the surface of the sun, we see granules which are of the order of 1,000 kilometers. We see magnetic fields in the lanes in between the granules with their order of 20 to 50 kilometers. The granules themselves are on the order of 1,000 kilometers. Active regions are on the order of 100,000 kilometers. And the time scales for convection varies from minutes when you're close to the surface to a month when you're down at the bottom of the convection zone. So it's not possible to model the whole thing as one single thing because of such disparate time scales. So some people model the interior. I've been modeling the surface, but even there's a wide range of spatial and temporal scales. So what we do is we solve the magneto-hydrodynamic equations, the conservation of mass, of mass, momentum, and energy, and the induction equation for the magnetic field, and the equations for the radiative transfer. So we're using a finite difference code we call stagger. It uses 6th order centered finite differences. It uses a 3rd order low memory Runge-Kutta time advance. We are assuming local thermodynamic equilibrium, so we have a tabular equation of state that includes the ionization and excitation of hydrogen, helium, and all the other abundant elements as a function of log density and internal energy per unit mass. The radiation is actually done in 3 dimensions, and we use, in order to simplify things a lot, we use a 4-bin opacity distribution function. We use a sort of hyperviscosity for the diffusion in the momentum and energy and induction equations, where we enhance the normal, we start with the diffusivity, we start with the viscosity, which has a term proportional to the propagation speed, the fast-most speed in this case, and another term that's proportional to the magnitude of the fluid velocity, and another term that's proportional to the compression to take care of shocks. And then that's enhanced by the ratio of the 3rd order differences to the 1st order differences to make the diffusion largest, where you have the wiggles, which we're trying to get rid of to keep the numerics stable. And we're working on a staggered grid, so we have to use 5th order interpolation. So we have the 6th order interpolations and the 6th order finite differences, 5th order interpolations. We work in index space with then using the Jacobian of the transformation back into physical space. And the main challenge is the radiation transfer. Radiation transfer is three-dimensional. It's very non-local because the photons can travel larger distances, so there's a lot of communication. Several people have tried different ways of handling this. Some people use short characteristics, but that's a very diffusive procedure. So we're using long characteristics, and so they go through the entire volume. And so you need to communicate a fair bit of data. The way we handle this is two things. We try and restrict the communication by only including the surface layers where, in fact, the photon mean free path is not that short, and there really is significant radiative transfer. And we don't bother with the transfer down deep, where, in fact, the numerical diffusion in the energy equation is far larger than any radiative transfer. And we restrict the number of frequencies or energies and the number of directions of the rays that we include. So we include one vertical ray, and then we include 4 slanted rays. And the slanted rays are rotated every time step by an incommensurable amount. So they sweep out over several time steps. They sweep out the entire volume. And for the opacities, we bin the different frequencies according to the strength of their opacity in 4 bins. Actually, we've also worked out a method. If we want to get really precise comparison with observations, it takes 12 bins. But for most of what we're doing, 4 bins are sufficient. For the boundary conditions, it's periodic in the horizontal directions. In the vertical direction, we extrapolate the log of the density at the top. At the bottom, we fix the magnitude of the density in the inflows. And in the outflows, we have the density go to either an average density or the fixed density, same as the inflows. The velocity at the top we take to go to a constant at its value at the last physical point. We use ghost zones, so we can use the same formulas in the boundary layers as in the interior. At the bottom, the velocity, we impose a zero vertical derivative. For the energy, at the top, we make the energy per unit mass go to its average value, and at the bottom, we extrapolate the energy in the outflows, and we fix the energy per unit volume in the inflows. For the magnetic field at the top, we make it tend towards a potential field. At the bottom, we advect in horizontal field. And we're assuming, we're trying to model the horizontal field coming in to represent the large scale field that the global dynamo would produce. So we take the field to be horizontal and uniform and untwisted. We've looked at 2 cases so far, a weak field of 1 kilogauss and a stronger field of 5 kilogauss. And these are at the bottom of our domain, which is 20 megameters deep. And this domain is only about, it's about 10% of the thickness of the convection zone, but it includes 2/3 of the scale heights. So we're including most of the stratification effects. And the boundary conditions can't be imposed directly on the magnetic field. They're imposed via the electric field, so we maintain div B equals 0. Now for the simulations, the thing that's really varying is the magnetic field, its strength and its geometry. And so there's sort of 2 pieces to my part of this project. One is we've been doing simulations, and I'll show some results, in a domain that's 20 megameters deep. But I'm trying to extend that now to 30 megameters, so there'll be an overlap with the people who are doing the interior dynamo simulation, so we can take values from their simulations but away from their boundary, so we're not affected by boundary effects. And then we'll use these results from these dynamo simulations to impose, instead of this constant horizontal field, we'll have a spatially and temporally varying magnetic bottom boundary condition. So to show what the field looks like as it emerges through the surface. This is the vertical field, and the two polarities are represented by the light and the dark. You see they come up in a very mixed polarity region here in the middle, and then they counter-stream into opposite polarity field concentrations. And that's typical how the magnetic field emerges on the sun. So this is from the simulation, and again it's the same kind of thing of the vertical field, and the white and dark are the opposite polarities. And again you see the field is emerging with this mixed pepper and salt kind of pattern of the opposite polarities, which are counter-streaming into these separate flux concentrations. And one of the interesting things is that this one is rotating, as is observed for some of the sunspots. What we've done to try and understand what this process is like is to try and trace the individual field lines in time. And that's very difficult because we're only saving the data at 1-minute intervals. So when we try and do that, you'll see some things jump around. So looking down from the top, this is one of the flux concentrations or flux systems that's come through the bottom. And even though these individual field lines are jumping around, what you can see is that the overall structure, you see these serpentine loop patterns where the downflows have pinned down the field, the upflows have brought the field up to the surface, and the convection has also shredded this large-scale field into these small filaments, which when they come up through the surface is what produces this small-scale pepper and salt pattern of opposite polarities. But as the loop emerges up through the surface and moves up into the atmosphere, what you're left with are the legs of this loop, which have the opposite polarities, and so you're left at the end with just the opposite polarities of these loops. The other interesting thing to notice is that one leg here is pretty coherent all the way down to the bottom of the box. The other one, you see, separates into several individual strands which rotate around one another. And those are actually the two basic models that have been made for sunspots. One as a coherent structure, and which was the original picture that people had, and the other as a spaghetti-like structure, which was first introduced by Eugene Parker. And what I conclude from these simulations is, in fact, both models are correct. They just apply in different situations, and you have both kinds of sunspots someplace, somewhere. And finally, these results are going to be part of a general presentation for planetarium that's being put together by the people at NCSA, of which this kind of flux emergence will be a little part. Bah. There we go. And so it starts off looking down from the surface of the sun, and the light and dark are the light of the hot upflows and the dark of the cooler downflows. That's the granulation pattern. And then we dive below the surface, and these blue lines now come from the same data set that I showed you before, which is the magnetic field, the magnetic loop, which is moving up to the surface. And if I understand correctly, the audio is in the process now of being added to it, and I expect within a couple of months the whole production will be finished. And I know that there's already, I was told there's a planetarium in France that wants to show it, and there's negotiations to show it at the Air and Space Museum. So thank you very much.